that blocking assignments are for combinational logic and non-blocking are for sequential logic. And I want to give you some examples to illustrate why that is so highly recommended. So I want to look at a simple program here. So I've got blocking assignments in there. TA is going to be equal to A or B. TB is going to be equal to A and B. And so if these are blocking assignments, this has to finish execution before that one starts. So if I look at the synthesized circuit, that'll give me TA. And I'm sorry, should be a C. And that should be a T. So TA is A or B, TB is TA and C. There's TA. There's C, and there's T. Okay, so that synthesized circuit makes sense based on the code that we've written. But what happens if I had done this? The question is, would you get the same circuit? What do you think? Yeah.
I don't think so. I think that you have a separate, like the TA would be coming in at the same time as A and B. In the sense that you have IPs or.
No. You're along the right path until you start going IMPs. This is going to execute and finish before this one executes. What happens here? You record the right-hand sides, and then the left-hand sides update when you hit the end. This is going to use the old value of TA, not the current value. TA will get updated here, and the updated value appears on the right-hand side with the blocking assignments. That's not what happens here. You get the old value. Now, the next time you come into the loop, that value there will have been updated. But you can see, does everybody see how this gives you the old value of TA? Since it's the old value of TA, that implies that you're going to have some storage for that old value. Which means you're not gonna get that simple, intuitively obvious combinational circuit. So this is a good example to show why blocking assignments for combinational logic gives you what you probably intended with that particular coding. So now, incidentally, on this one here, what changes do you think you should make to this code to give you the same behavior as this code? What changes would you make here? Yeah.
You put a delay in front of the second.
Now, delays aren't synthesizable.
Couldn't you just change the arrow to equal just on the TV?
No. Other than changing the non-blocking to blocking.
Different block.
What you could do is put TA or T and TB also in this event list.
Oh.
Because then, when you get to the end and you update, TA will have changed, you'll go through the loop a second time. And that way you'll get the right value. But that's kind of convoluted. I mean, this makes more sense if this is the type of circuit you intended to be synthesized. Yeah?
Can you show us what the synthesized circuit would look like for that second code?
Oh, gosh, no.
Goodness, crazy mess.
It would be a crazy mess because there would obviously be more gates because this TA now would have to be an input to circuitry determining new value of TB. So you'd have more gates. I'm not sure exactly what the synthesized circuit would look like. Certainly it would not be as simple as this, which is kind of intuitively obvious of what you intended with that particular code. So the problem is that the non-blocking assignment doesn't always follow the logic flow that the data flow level of abstraction gave you. Yeah.
Could you flip one more time why putting the TA or TB in an always statement will change the code?
Well, the reason why it gives you similar behavior is, let's suppose A changed. So I enter the always loop, I record the right-hand sides, but TB is going to use the old value of TA, not the current value. You hit the end, both sides update, the left-hand sides, so you go back in again. When you go back in again, the value from the previous time is what gets used on the right-hand side of that equation. Yeah.
What would happen though if you changed both A or B and C? Because then wouldn't the TV value change the first time through the loop?
Oh, yeah, my only point was illustrating when you have a left-hand side variable that appears on the right-hand side in the same block. That shows that just going once through with non-blocking assignments does not give you the same result that you would get with blocking assignments. And that was the only point in showing that. So this provides some justification for using the blocking assignments for combinational logic. It's more likely to match the data flow description that you put down, yeah.
And would this count as an example of latch inference? Or is this kind of separate?
Probably you would have to have a latch in there because you're using the old value of TA. So I would, well, remember one of the causes of latch inference is using a variable before it's been defined. The first time through the loop, you don't have a definition for TA. So that would imply latch inference. Okay, so now, so why do we want to use non-blocking for sequential circuits? Well, you don't run into the same kind of problems that you would with the using the non-blocking assignments for combinational logic. And this kind of depends on the semantics of what you're trying to do. So let me show you this simple example here. I'm going to define two always loops. Now, those loops are both triggered on the same event, the positive edge of the clock. In the first one, I'm going to set A equal to data, and in the second one, I set data equal to a variable B. What I mean by the semantics here is this obviously, if you look at the final result you get, this obviously is going to depend on which one of those executed first. Order would be important. Now, yeah, you could do something like put a # delay in this, and that would give you an order that this would finish before that one does. But again, the # delays are not synthesizable. So what this illustrates is what is referred to as a race condition. And what we mean by a race condition is you've got two things that are competing at the same time, and it's not intuitively obvious what ordering there is, and so both are trying to complete at the same time, and it's not intuitively obvious what you would get from this type of result. So, the way that you would avoid the race condition is to replace both of those blocking assignments with non-blocking assignments. Because now what's going to happen is these would both execute at the same time, but I'm recording the right-hand sides. And then when I get to the end, I'll do the update. Yeah.
Did you intend to just have data equals B and not data greater than? Okay.
Now I'm going to record the right-hand sides. Actually, if I had replaced this, if I had left it the way it was, I would have some ordering, because this would have to complete and this would just do an update on the current value. So it shows you that you can avoid the race condition by using the non-blocking assignments. Now, I'm going to show you an example. I had made this statement before, that you want to register the outputs of your modules because it'll be easier to do the timing analysis. And I'm going to show this with this particular design here. So I've got several modules here, and you'll notice that these outputs are not registered. So if you look at the module A, it says that this output logic here has a 3.5 nanosecond propagation delay time. And I'm going to assume that the clock for this circuitry that's clocking these registers has a 10 nanosecond period. And for simplicity, I'm going to assume that setup and hold time on these registers is 0. So we can see that we have a 3.5 nanosecond delay time here. This output feeds into module C, and this input logic has a 6.5 nanosecond propagation delay. So if these are clocked at the same time, and I assume the setup and hold times are 0, then I can clock these at 10 nanoseconds. And you can see that the total propagation delay between the output of this register and the input of this register is 10 nanoseconds. Not a problem. The A module also feeds down here to the D module. Again, the input logic has a 6.5 nanosecond propagation delay. So a 10 nanosecond clock doesn't pose any problems. But now look at this module B here feeding into module E. Module E also has a 6.5 nanosecond propagation delay for this input logic. So there's no problems with respect to module A driving any 3 of these modules. But now look at this one. This module B has a 5 nanosecond propagation delay, which means that if you're going to use a 10 nanosecond clock, this would have to have no more than a 5 nanosecond input propagation delay. Otherwise, you're going to have to increase the clock period to 11.5 nanoseconds. If these were registered outputs, the time from the output of this module to the input of this register would only be 6.5 nanoseconds, and I could actually have a faster clock. It's also a lot easier for the synthesizer to do a timing analysis on your circuit, because you're going from register through combinational logic, and it's easy to figure out what the propagation delay there is going into the next register. So registering the output can lead you to a lower clock period, and it's also easier to figure out what the timing is from one module to another. So this is a good example of why registering your module outputs is a good idea. Now I want to go back and review something from 172. Yeah.
When I was doing the homework assignment, I read something about that, and it said, placing the registers on the module outputs also simplifies the compilation process because timing budgets aren't needed. Is that kind of what you were saying about how it makes the timing simpler?
Yeah, it's a lot easier to figure out the timing. We're going to be talking a little bit later on in this course about timing reports that are generated from the synthesizer and how you would specify timing constraints. And it's a lot easier to analyze the timing for the synthesizer if every module's got a registered output. So I want to review something from 172, which is the renumbered 271. And the reason why we're reviewing this particular topic will be obvious a little bit later in today's lecture. I have a combinational logic here, circuit here. This is a 2 to 4 line decoder with output polarity control. What I mean by output polarity control is on a standard decoder, 2 line to 4 line, one and only one of these outputs is going to be asserted. Which one is asserted will depend on the binary pattern that you have on I0 and I1. So if I have 0, 1 is the input, Y2 will be asserted. If I have 1, 1, Y3 will be asserted, and the others will be not asserted. Now the question is, what do I mean by asserted and non-asserted? Is that logic 0 or logic 1? Just as a quick review, if I make this input here a 0, then Y is going to equal A. Whatever A is what Y is going to be. However, if I make this a 1, then Y is going to equal A bar. It's just an inverter. So by controlling whether this is a logic 1 or logic 0, I can determine whether this exclusive OR gate operates as a buffer or an inverter. Okay, so if I took the Y's off of the output of the AND gates, then the asserted output would be a logic 1, and the rest would be logic 0s. This allows me to redefine that if I want to. By making this polarity a logic 1, that puts a 0 on all of these, and so the asserted output would be active high. If I change this to a logic 0, that puts a logic 1 there, and then I can have my asserted value as a logic 0, and the rest will be logic 1s. So all this does, along with the exclusive OR gates, is allow me to define whether I want my asserted output to be a logic 0 or a logic 1. And the other 3 outputs would be of the opposite logic state. I have 3 inputs and 4 outputs. I can implement that 2 to 4 line decoder with a ROM. Actually, I could use the RAM or any other type of memory device that you want. The inputs I0, I1, and polarity would go into address lines of the memory chip, which would then access a particular memory location. And the data I store in that memory location is what 4-bit output I want for that given input condition. And it turns out that any combination logic circuit. Can be implemented this way. As another example, let's suppose I want a y1 to equal A or B or C, and I want y2 to be equal to A exclusive or C. So I have three inputs. So I have 0, 1, 1, 1, 1, 1, 1, and for y2 I'll have 0, 1, 0, 1, 1, 0, 1, 0. So what I could do is have a ROM. So this will go into address A2, address input A1, address input A0, and I'll have two outputs. And this will be, let's say Y1 and Y2. So Y1 is D0, and this is D1. And these are memory locations. Data in each location. So you just store in the respective memory location what you want the outputs to be, and you can, as you can see, take any truth table, which you can always derive from Boolean expressions, and implement that in a ROM or any type of memory device. Now, when you use a memory device in this particular way, we're going to give this a special name. They're called lookup tables. Or a LUT. So a memory chip used to implement combination logic is referred to as a LUT. All right, so now I want to talk a little bit about the architecture of an FPGA. And this is a very simple FPGA, but it'll be good enough for a initial introduction. You look at his shirt, you can see that the material, it's got a pattern on it. It's a repeatable pattern. And the material that it's made out of, we call fabric, as just a general term, regardless if it's cotton or rayon or whatever it's made of. Inside of the FPGA, you have this huge block in here, and it looks like a lattice of, these are configurable logic blocks, CLBs. Incidentally, that is a acronym I expect you to know. And it's a repeatable pattern, just like the pattern on his shirt. Well, if we call his shirt made out of fabric, this lattice of configurable logic blocks is commonly referred to as the FPGA fabric. So when they're talking about the fabric of an FPGA, they're talking about a lattice, a matrix, if you will, of configurable logic blocks. We'll see what a configurable logic block architecture looks like shortly. It turns out that there are three things that you program when you program an FPGA. One thing is you're going to program in the functionality of all of these configurable logic blocks. What are they going to do? Maybe you're going to build a counter circuit or some other type of circuit. So I need to determine what the functionality of the configurable logic blocks in this FPGA fabric is. That's the one thing you got to program. These little blocks here on the outside are input-output pads, and they have some circuitry in there as well. I may want an output, for example, that's registered. I may have an output that I want to be tri-statable. So there's circuitry in there I can also program to define what my output's going to look like. The third thing that you have to program is the interconnection. You got to hook everything together. The input-output pads have to bring signals into the configurable logic block where the data is going to be processed in some way, and the outputs of some of these configurable logic blocks will go through output pins, so you have to interconnect the outputs of these configurable logic blocks to some of the I/O pins. So the three things you program. Are the configurable logic block functions. The input-output functions. For example, a registered or non-registered output. And the interconnection network to hook everything together. Hook I/O pins to configurable logic blocks, configurable logic block outputs to input-output pins. This is a product specification document that I got from Xilinx. It is admittedly old. It's from 1999. The reason I like it, however, is this talks about the Spartan family of FPGAs. These are still widely used. But the reason I happen to like this application note is it gives a very good basic introduction to what a very simple FPGA looks like. So it's a very good introduction so you get some feeling for what this internal architecture looks like. So I want to go through this. This is available on D2L, so you can download a copy, and of course this will be in the lecture notes as well. Okay. In the Spartan family of FPGAs, these are the different types of devices. This says logic cells. Not sure exactly what that means, but it's irrelevant anyway. Max system gates. This is a metric that which not used so much nowadays. It's kind of useless information. It works under the basis of any digital logic circuit can be implemented solely with 2-input NAND gates or 2-input NOR gates. So what this says is that an XCS05 can implement any circuit that could be implemented with 5,000 of those 2-input logic gates. Why I say this is somewhat of dubious value is I have no idea of what you can actually build in terms of circuit complexity with 5,000 2-input NAND gates. For example, if I wanted to build a simple microcontroller, I don't know how many logic gates it would take to actually build that thing up. So, here's the configurable logic block matrix, the FPGA fabric. This is how it's organized. So the O5 has 10 rows and 10 columns of configurable logic blocks. The XCS40 has got 28 rows and 28 columns of configurable logic blocks. And for those of you who attended the public school system and never learned how to multiply, they give you a column that tells you how many total configurable logic blocks. So 10 times 10, for example, is 100, in case you didn't know that. It also tells you the number of flip-flops that are available in the device and the maximum number of input and output blocks that you have. So this is rather simplified, but it shows you what the internal architecture looks like in a little more detail than the figure that we just had. So here's my matrix of configurable logic blocks. Here's my input-output blocks. And this in here where it says routing channels, that's that interconnection network I was talking about. Now, this particular FPGA does have some resources that you can use outside of the FPGA fabric, and there's 4 of them. This supports boundary scan, if you want to do boundary scan testing. There is an internal oscillator on the chip. There is a startup circuit block that will generate a pulse when you apply power so you can initialize the device. And then this block is a readback block so that you can read back the information that you use to program the device, that bit file that you download. This is what the configurable logic block architecture looks like. First thing you will notice is, unlike programmable array logic devices, the PALs, the generic array logic devices, the GALs, there ain't no logic gates in there. There's no AND gates, OR gates, exclusive OR gates, etc. But you will notice these 3 blocks, and these are LUTs. The way that you implement combinational logic circuitry in FPGAs, unlike simpler programmable logic devices, is by programming the LUTs. So the configurable logic block has got in it some LUTs. In this Spartan family, you get 2 registers, and then you get some multiplexers in here that you can program to steer the data where you need it to go. So when I talk about programming the configurable logic block functionality, what I'm talking about is initializing the memory location contents in the LUTs, and we're going to look at some of the circuitry here. It's a little more flexible than what's shown in this simplified diagram. Every configurable logic block looks like that. Yeah.
So the maximum, so there's not really any gates in, the configurable logic block. But what is that, like the maximum system gates metric, the one where it tells you the number of 2 and 4 gates, that's also was configurable logic block, right?
No.
Okay.
That's just telling you the equivalent. For example, it's like saying, how many gates does it take to implement a latch? It takes 2 gates, 2 NAND gates or 2 NOR gates. So if I had a circuit that had 100 latches, that would be 200 gates.
Okay,
Right.
so that metric tells you the number of things you can, it's like equivalent of what you.
Yeah, but you should really ignore the number of gates because it doesn't tell you anything. Because again, what can you implement with 10,000 2-input NAND gates? I have no idea.
Yeah.
It was just a figure of merit to give you an idea that, let's see, if this FPGA has 5,000 gate equivalents and this one has 10,000, then I should be able to do twice as much with the latter one. Okay, but that still doesn't tell me how complex a circuit you can build. If you look at the LUTs, they are relatively small. LUT G and LUT F. How big are those memory? 16 by 1. So that's not very big. You will notice, however, that the output of the GLUT can go over here through a multiplexer and directly into the register. You can also go through this multiplexer and it becomes an input to that LUT. So you can cascade LUTs to get more complex expressions, yeah.
Where are the control signals for those multiplexers coming from?
I'm sorry?
Where are the select bits for the multiplexers coming from?
That's part of the programming.
Okay.
When you program, and I was just getting to that, one of the things you obviously have to program is what's the LUT's content. The other thing that you're gonna program is what are the select lines on all these multiplexers that you see. When we get to this circuitry here, you're gonna see that you have a couple of other options. This is a simplified diagram of those registers, but we'll get to that shortly. So you do have the capability of going from a LUT into the registers and getting a registered output. If you trace the F LUT, if I trace the F LUT, and if I choose this upper input, I can get a combinational output from this configurable logic block. So you can get combinational outputs, you can get registered outputs, depending on how you program the multiplexers. This figure 3 here shows a little more detail of that register. And you actually have quite capability on this register. First of all, you'll notice here's your clock. What do you think that much does?
Positive and negative.
It allows you to choose whether you want a positive edge or a negative edge trigger for that flip-flop, depending on which of these two inputs you use to drive the clock. You have a set or a reset. And if you look at the top up here, you have a OR gate. And depending on how you program this multiplexer, you can either have some external signal come in to set or reset this register, or you can have GSR, which is a global set reset. Kind of like, remember that circuitry that was in the startup block? It generated a pulse when power was applied to the FPGA. That's what GSR is. So you could have that come in and set or reset your individual registers. Does this circuitry here look familiar to you? The Q output coming into a multiplexer or D coming into a multiplexer driving the D input. Have you seen that before? Probably not. How many have seen that before? Oh, good. Nobody. Sidebar. A free running clock is a clock signal that you apply power and you start getting clock pulses. And as long as you keep the power on, you're going to get clock pulses. All right, so let's look at some circuits here. First circuit. In this circuit here, your Q output is going to update on every clock. Well, maybe in your design, you don't want to do that. Maybe there's only certain periods of time in which you want Q to update on a clock pulse. So one of the things that you could do that's supposed to be an AND gate. Is to gate the clock. If you make CNTL a logic 0, even though that's a free running clock, you're not gonna get any updates on the register. When you make CNTL a logic 1, then the clock pulses from that free running clock are allowed to reach the clock input. And so they call this a gated clock. So by determining when CNTL is a logic 1, I can control when the Q output updates in the presence of a free running clock. That circuit, however, has a problem. Does anybody see what the problem is?
If the clock is high and then you switch control high, it might update.
Okay.
the clock.
The problem here is at that point right there, I'm gonna get a clock pulse. I don't want a clock pulse there. I want a clock pulse there, but not there. So that's one of the problems. So here's your preferred solution. Go ahead and hook your free running clock up to the clock input. But I'm gonna have a multiplexer here that drives the D input. One input will have data, the same as this. The select line is what CNTL will have. But I'm gonna take the Q output and feed it around to the other multiplexer input. Now, let's suppose CNTL is a logic 0. Then the D input is going to be driven by the Q output, which means you're going to get clock pulses, but what's Q going to update to? Its current value. It doesn't change. When CNTL equals a logic 1, then data will drive that. This has no glitches. This doesn't have that problem. Okay? So, if you need to control when a register will respond to a free running clock pulse, that's the preferred solution, is to have a multiplexer driving the input and have feedback. You have a multiplexer that either takes data input or feedback from the Q output driving the D input. Now you can have a free running clock, which can be positive or negative edge triggered, depending on how you program those multiplexers. Okay? So that's the flip-flop functional block diagram. And you recall in the configurable logic block you had 2 registers in the output. Both of them have this type of circuitry there. So you can preset or clear them either with a special signal or globally, and you get your choice of either setting or clearing them, and you can control the clock edge. And this will support only clocking the register at certain times. You have a similar type of circuitry for the input-output blocks, so that you can register inputs or register outputs, and they have this same sort of circuitry as we saw before in the configurable logic block. But this is what the circuitry actually looks like. For the input-output blocks. This package pad is a pin on the FPGA. You have an input buffer, and this can go directly in for a combination logic input. Or you can register the input and have that go into the configurable logic block, the FPGA fabric. On the output, you'll notice that you have a couple of options. This is your output register. You'll notice you have a Q, but not a Q bar output. However, notice on the input to that register, you can choose an inverted or non-inverted input to the register. So you effectively have a Q and a Q bar output, depending on how you program that multiplexer. You have a tri-state buffer on the output, and you can either globally activate them, or you can activate it with this signal T, and you can make that signal active high or active low. So you have a tri-state output capability. This also has a programmable pull-up or pull-down network, so you do not require external to the FPGA pull-up resistors or pull-down resistors. They're provided inside the chip. Let's take a 10-minute break. Come back and we'll talk about the routing.